Thank you. Kia ora, ko weji toku ingoa, no marihia o ku tipuna, ke te nohu au ki te whanganui a Tara. Hello everyone, my name's Weiji, originally from Malaysia and currently based in Wellington, New Zealand. Today I'll be talking about accelerating GeoTIFF readers with Rust. And yeah, let's get started. So GeoTIFFs, I don't think I want to explain GeoTIFFs. Most people should know what GeoTIFFs are. They are the most common raster format based on GDAL's 2024 user survey by a long shot. And today I'm going to cover Rust-ish libraries, but yeah, there will be like 3 libraries I cover today. First one is the libTIFF driver, which is this multi-threaded and thread-safe driver that's present in GDAL 3.11 plus. I'll touch on async-TIFF, which is a library that my colleague Kyle and a few others from development suite have been working on. It's an asynchronous TIFF reader built completely in Rust. And because I'm actually a machine learning engineer at development suite, so I work with like GPUs a lot. I've been playing with this like NVTIFF sort of driver that NVIDIA's put out, which can read and write TIFF using the GPU. So I've been playing with that, and yeah. And this talk, I'm just going to focus on the reading and decoding parts to either CPU or GPU memory. But there's a whole other part, which is, I guess, writing, if you want to write in parallel, which I won't cover today. But yeah, so just reading and decoding today. Okay, decoding a GeoTIFF. GeoTIFF kind of looks like this. There's like metadata headers and on the top, and then you have these like image file directories or IFDs at the bottom. The metadata header kind of points to these like IFDs somehow. You can sort of decompose how GeoTIFF decoding into 3 components. First part is probably like you want to read the GeoTIFF from either like your local disk or somewhere on the like a HTTP request, S3 bucket, whatever, across the network. On the CPU side, in GDAL, for example, you would read it using something like libcurl. On the Rust side, there's crates as so crates in Rust are what we usually call like libraries. Object stores, like a popular one people use for that. If you're doing like GPU type stuff, Quick IO and QFile from like NVIDIA, these are libraries that allow you to read bytes across the network into like the GPU directly. So that's sort of like one component you want to have. There's also like the decompression of raw bytes. So usually the GeoTIFFs are compressed, and then you would use on the CPU like libraries like libTIFF, or on the Rust crates, there's like, depending on your compression type, you might use like Flake2, Weasel. I don't know, there's like probably like a dozen other crates where you can do the decompression of the raw bytes. And on GPU side, there's like NVComp, NVJPEG, and these sort of like do the decompression on the GPU. And because we're working with GeoTIFFs, there's like some GeoTIFF tag metadata stuff, which is you need to parse in order to understand the data properly. This is handled again by these like sort of libraries. GeoTIFF, async-TIFF kind of has some of these like GeoTIFF parsing stuff right now. NVTIFF as well from NVIDIA has some of these, like you can pass like GeoTIFF tags, and obviously the data stored in the GeoTIFF. So these don't kind of go in order, but these are like, sort of like the 3 main components you might have. And typically you would bundle all of these like sub components together. For example, GDAL combines like libcurl, libTIFF, libGeoTIFF. This super simplification, GDAL does a lot more, bundles a lot more things together, but you know, at least this is like sort of the minimum, I guess you can think of. And same with like the Rust and the GPU stuff, you would sort of try and bundle some of these 3 components together to decode a GeoTIFF. Right. The talk's about accelerating GeoTIFF reading. So what do we want to accelerate? There's sort of, I can see sort of 4-ish like ways to accelerate things. The first one is to speed up the network transfer part. So look into, libraries like Opstore or like QuickIO's Remote IO, where you can read into the GPU. So this is like sort of speeding up the transfer from the network. Number 2, there are some tricks you can sort of do. Obviously, try and cloud optimize your GeoTIFF. Have all the metadata in the header, and then you can fetch like the first, I think, 32 kilobytes or something. There's also like some libraries, like Rasteret is a Python library where you can sort of store you would parse the TIFF header once, and then you store it like in a Parquet or somewhere else. TIFF is like another initiative that is trying to do that with like C++ code base and with bindings. Virtual TIFF ties into like the virtualizar ecosystem. They kind of have like something similar, and the idea is like, parsing the header could be slow, so let's put it somewhere else where you can access it fast. I'm actually not going to cover the first 2 today. I'm going to talk on the number 3 and 4, which is how we could decode. So once we've kind of dealt with the metadata, like you've parsed the metadata, and you know where the tiles are within the GeoTIFF file, we want to find how you can like decode these like tiles in parallel, or do the decompression in like a fast way. So it could be like multi-threading, async, GPU accelerator, whatever you want to call it. It's like, I'll cover like these 3 libraries, but that's sort of the general idea, decode things in parallel. Touch a little bit on hardware accelerated decompression. So if you can make use of like either CPU, like SIMD, single instruction, multiple data instructions. Those make things like a lot faster if you have like a lot of data to process. And obviously the GPU can do a lot of things in parallel as well, depending on what sort of GPU you have. So libraries like Zune JPEG is like a Rust crate that does a lot of like these SIMD sort of instructions if you have like JPEG compression. Or on the GPU, there's like NVJPEG, NVComp, these sort of things. So I'll just cover like the last 2 here. But ideally, you want to like optimize all of these like components to get like the maximum possible acceleration. Okay, I'm going to run through some benchmarks. So we're going to look at the Sentinel-2 true color image, RGB tree band. It will be like a uint8D type. This image is taken over somewhere over Kenya. Originally came in a deflate compression and 318 megabytes. I've converted it into like a tiled GeoTIFF. So apply LZW compression, set predictor level 2, predictors 2, sorry, horizontal differencing, block size 256, which is like the default. This is like the fancy GDAL 3.11 command line way to do it, instead of like using, GDAL translate or something. So this is, I've got the code somewhere if you guys want to test this later. But so I'll cover 2 benches, one reading to CPU, one to GPU. On the CPU side, I'm just going to compare LibreTIFF, which is this GDAL new multi-threaded driver, and async TIFF. Note that this is reading from like, I benchmarked this on my laptop, so not over network. So this is reading from this into like CPU memory. With like 16 threads, LibreTIFF takes, you get about 1 gigabyte per second throughput. And then async TIFF version Pi v0.2.0 takes you get about 0.6 gigabytes per second throughput. So that translates to about 0.26 seconds for reading that sampled GeoTIFF I mentioned just now. And 0.45 seconds for async TIFF. And I've also shown like some single-threaded performance and 4 threads on async TIFF. I couldn't quite get 4 threads on LibreTIFF to work. There's some bug where it's either like 1 or 16, so I didn't managed to get that up. But I should file a bug report at some point. But yeah, if you want to look at, if you want to do this in Rust, this is sort of how you would read it. You can actually use GDAL has bindings in Rust in this GeoRust GDAL repository. So this is sort of how you would do it. You would, pass in the GDAL options into this dataset options thing, and then you can read, iterate through like the bands you want. I've got the code in that repo, which I'll share later if you're interested. So this is reading to CPU memory. Next, I'll cover reading to GPU memory. So if you're using like NV-TIFF, it takes about 1.6. It'll give you like about 1.66 gigabytes per second throughput. So which is a bit faster than the, well, maybe not a bit, faster than the libRTIFF driver, which is again at about 1 gigabyte per second throughput. So this means it takes about 0.16 seconds to decode the GeoTIFF. And if you're doing this in like a machine learning sort of application, the data's already on the GPU, which is sweet. You can do like your whatever algorithm you have on the GPU, be it like machine learning or some GPU accelerated, sort of calculations. So, and this, notice that libRTIFF, so there's a little bit of overhead if you're doing like the decoding on the CPU and then doing the transfer from CPU to GPU, the host to device transfer as we call it. That's roughly in the 0.1 to 0.3 second, depending on, what sort of library you're using, how you're streaming it. This was benchmarked on an Ampere generation A2000 laptop GPU. That's sort of like the sample code I have so I've made this library called Cog3PO, which I'll talk about later. But what you kind of do is first 2 lines of code is you parse like the bytes. It could be from your file system, could be from network. You set up like a CUDA stream. So you set up on your CUDA GPU, CUDA enabled GPU, you set up like a CUDA stream, put it on like GPU 0, for example, and then you pass it into this like CUDA cog reader struct, pass in both the bytes and then the handle to the stream. And then I've set up this like DLPack thing where you can like read into like a DLPack tensor. And then that gives you like a tensor or multi-dimensional array. Again, code's there if you guys need it. How are we doing on time? Cool. So covered the CPU and the GPU side of things. How can we like speed things up? So async-TIFF is like a pretty new Rust library. We've been trying to get people maybe excited about it. There's some users of it already, but GDAL obviously has more features and more compatibility with like server types of GeoTIFFs. But if you want to like truly get I think some people think that Rust makes things fast, but there's also like a lot of steps you can do, and we slowly have to like implement those things to be as fast as GDAL. And then also all of the GeoTIFF, like I don't know, there's like so many different things within the GeoTIFF that little nitty-gritty things you can do. But for the case of like speeding up reads, we probably want to look at more efficient decompression algorithms. So async-TIFF, right now it actually allows you to pass in your own decompression algorithm. There's like a registry you can pass in your own thing. So that could offer you some speed up. We should probably look into like SIMD type instructions where you can utilize some features of your CPU that most people don't actually utilize. libRTIFF has some of that, GDAL as well, but we haven't really implemented that in the async-TIFF Rust crate yet. But once we have that, we might more match what GDAL has. GDAL's like libRTIFF in particular. On the GPU side of things, I want to emphasize that it's actually a good idea to let the GPU do most of the work. So if you could send the compressed bytes directly to the GPU, so don't do decompression on the CPU and then send those to the GPU. send the GPU like compressed bytes, let the GPU do the decompression and decoding, and let it do the work. It's an expensive device. You want it to use it as much as possible. If you can do that, that will give you like lots of benefits. If you're using if you have a lot of money and you've got these like newer chips like the NVIDIA A100s or the Blackwell sort of generation chips, there are like some hardware decoders built into the GPU itself, which can support like certain like compression codecs like JPEG, NVJPEG and NVCOM. They have these like sort of hardware decoder engines which offer even more speed up, but you do need to have compressions that are supported by these libraries to use that. But that would give you possibly like the maximum level of acceleration in terms of reading GeoTIFFs. Okay, cool. And I guess not everyone uses Rust here, so I've been like trying to build out this like Cog3PO library to have like both high-level Rust and Python bindings. Two main things I am kind of like focused on is I want to decode things into like this dlpack struct. So I think of dlpack as, if you think of like Arrow for like tabular data, it's kind of standardized the whole thing. dlpack is what is like a common interchange format you can use between like NumPy or QPy or PyTorch. Like for like QPy and PyTorch are these like GPUs of libraries. So what you could do is like, if you look at the code on below, you can from Cog3PO import cog reader and then pass in the path to your cog to this cog reader. So and that will give you like this dlpack capsule, which is like a bit of an opaque thing. But NumPy has this like from dlpack thing most people have never heard of, which can read this like capsule, which was created like in Rust, and then you can read that into a NumPy array. I've also got integration plans with X-ray. You can like do X-ray open data array, pass in the path to your TIFF, set engine equal Cog3PO, and that should read things into like an X-ray as well. So that's available in that repo there. On the GPU side of things, similar sort of API I'm trying to do. So you do from Cog3PO import Q.cog reader, and then pass in the your cog file to the cog, or if you have like network, you can do that too. And then you can do either QPy from dlpack or Torch from dlpack. So it's very similar API, which is the beauty of like dlpack in essence. And I've sort of like some ideas of how to integrate this into like QPy X-ray, which is like how this like X-ray library that reads things into QPy, but haven't quite worked out that yet. It might be similar to the sort of API before, but to be done at some point. Cool. And so future plans, if I've got sort of two, there's a lot of work to do still if we want to, enable like fast decoding of TIFFs purely in Rust. If you want to fund us, talk to me or one of my colleagues. We're keen to get more people excited about async TIFF for the CPU side. And me personally, being like a machine learning engineer, I care more about the GPU side of things. So like QFile, NVIDIA GPU direct support. So if you can stream data directly into the GPU, that's something I kind of want to work on. I'm also thinking of like this, I've read some things about like modular recently, where it's this like new language where you can do a lot of like GPU programming, not just for like NVIDIA chips, but for like AMD GPUs or like Apple Silicon chips. So imagine like if you can decode, really like leverage your hardware, the hardware you have, be it like a Mac or a Linux or Windows computer, like really use the hardware to decode like GeoTIFFs fast. So let's see if we can make this happen. Slides and code are at that URL, or you can scan the QR code, or email me about this. Oh, and one more thing, we have this like GeoRust sprints on Saturday and Sunday. If you're keen, look up the schedule. We might have something to, have some time to hack on this together. Cool. Thank you, Kira.
Does anyone have any questions?
Hello, thanks for the great talk. So I'm curious, you've implemented a lot of things in Rust, and then you make Python bindings for the Rust code that you've written. I, being a Python developer, I look at Rust and I'm like kind of scared, right?
Yeah.
Yeah.
I was too.
Yeah. Okay. That was one of my questions, is it really that scary? And also, like, are you making these Python bindings so that it's more readily usable for a lot of users just because more people are using Python? Or is there some other reasons why you would have Python bindings?
Yeah, so for context, I only started learning Rust last year, so I'm not very good at Rust yet. But this was actually more like a pet project for me. Okay, I want to learn Rust, and then I want to read GeoTIFFs as well. And so this now is taking over my life. But to answer your question, I still see, I think it's the Python bindings, it makes it more accessible for people. So that's where I'm going with that. The X-ray part in particular, I'm a heavy X-ray user. So I kind of want the bindings to have that X-ray interface. There's nothing quite like X-ray yet in Rust, as far as I'm aware. And X-ray, you can visualize what the data looks like, the coordinates, all of that. There's not quite something like that yet in Rust. I don't want to build that in Rust either, but that's kind of why I want to tie it back to Python. And most of for me, machine learning is mostly done in Python still. So I kind of have to bring it back to Python, which is the motivation for me. Maybe and if it helps everyone else, it's better. Cool.
Any other questions? Thank you for coming, and thank you for presenting.